Greetings, my name is Matthew, and welcome to a conversation about related rates. In this video, I'm going to go through some example problems which range from working with equations that don't necessarily have variables associated with them, just x and y's, and then we'll move into some questions, or rather some examples, that are word problems, so we can be paying strict attention to what it is that's actually changing with respect to a number of different variables, sometimes with respect to time, sometimes with respect to units. And what's happening in related rates problems is we're taking our previous conversation in the previous video about implicit differentiation to the next level. And we're doing that in a way because we're taking the derivative of equations with respect to a variable that is not necessarily present in the original equation. How do we do that? Let me show you. So as usual, I'm not going to talk through every bullet and every note that's present in these slides, but you are more than welcome to pause and take a look at all of this stuff. One thing that's being mentioned here is that time is often present implicitly in a mathematical mode, or I might say a mathematical model. So especially if we're talking about cost analysis or revenue or profit, or in a physics class you might see an example of where you've got projectile motion and the height or distance away from another object, or a starting point is changing. And all of those things change over the course of time. So time is somehow inherently always one of these things that's changing in whatever scenario it is that we're describing. So implicit differentiation becomes very valuable when we're trying to make sense out of those models. And as usual, well, not all of you know this, but I don't ever read what's in these. Maybe not ever, but I don't usually read what's in those gray boxes or those sand-colored boxes. Sometimes I do, but often I don't. And the reason I don't is because I want you to be able to read those and get a slightly different perspective than I'm presenting, so that you've got a couple of perspectives that you can maybe extract out of these videos, and then you take 20% of one and 80% of the other, or vice versa, or 60-40, and you put it together in a way that's going to be most beneficial to you. These notes or slides that I'm going through were originally created to go along with a textbook, a calculus book that was published by Pearson, so that's why you're seeing that note there. Pearson is a publishing company that I've used their books for a long time. They put out a lot of great material. And in this first example, we're seeing that we're to assume x and y are functions of time. So whereas usually we see something, the kind of notation like f of x, which means f is the name of the function and time is x is the independent variable. So again, f is the name of the function and x is the independent variable. We're not doing that. In this case, x is a function of time. So x is the name of the function, and t, or time, is the independent variable. And as part of the same equation, we're going to be working with a function y, which is a function of time. And it's a little tricky because I'm not actually going to tell you what those two functions look like. I'm not going to tell you that y is equal to t squared minus 5t plus 1/2 or something. I'm not going to give you any of that kind of information. So it's going to be like I'm leaving you in the dark a little bit as we're going through this, but we're still going to be able to make sense out of it. So x and y are functions of time. We're going to be evaluating dy over dt for this equation, and we're being given these additional three pieces of information. So let's see what it is we can do with that. The first step in this process, at least the way that I do these problems, is I am going to take the derivative of the original equation. And remember, we're taking the derivative with respect to time. So let me zoom in here a little bit. I'll be working my way down the right-hand side of my page, as I take the derivative of this equation with respect to time, and in this first term we need to be using the product rule. So I like to leave the first factor, which is an x, and then multiply by the derivative of the second factor. So I'm taking the derivative of y with respect to time. Now this would look a little bit different if there were a 2 on here. If there were a 2 there, then the derivative of 2y would look like this: 2 times y times dy over dt. And this would be the chain rule coming into play. In this case, since it's not y squared, I should really just get rid of all of that. Since it's not y squared and it's just y, I'm taking the 1 that's the natural exponent there, I'm putting that in, I'm multiplying by y, I'm decreasing the exponent by 1, which makes it y to the 0, which is again equal to 1. So now I've got 1 times 1, which is why initially I didn't write anything. It's just 1 times 1. But then I do still have to multiply by the derivative of the inner function, which is y itself. And the derivative of y with respect to time is dy dt. That's not even really the derivative of it, because I don't even know what y is. So it's almost like I'm just putting down a note that says, if I knew what y really is, I would take the derivative of it. But I don't, so I'm just going to write down dy dt. It's very generic. Alright, now the second half of the product rule. So here's my plus sign. I'm taking the derivative of x now. But I don't know what x is. But I want to take the derivative of it with respect to time. And since I don't know what x is as an actual function of t, like we talked about right there, since I don't actually know what that function is, x of t, when I go to take the derivative of it, I'm simply going to write down dx with respect to time, derivative of x with respect to time, then multiply by my y variable, and then my second plus sign. So this plus sign is this one, derivative of x with respect to time, we just talked about that, is dx dt. Derivative of a constant is 0, so the right hand side becomes a 0. Now, we're evaluating dy dt. So say the instructions. And I see the dy dt right here. And then I see some other things. I see an x, I don't know what that's worth. I see a dx dt, I don't know what that's worth. There's another dx dt. And there's a y, I don't know what that's worth. But thankfully, this problem of those 4 unknowns really, let's say of those 3 other unknowns, x and y and dx dt, the problem tells us what those other 3 values are. They are -3 and 2 and 5. Awesome. So you've got some options right here, a couple of options anyway. You could take this equation and solve it for dy dt and make this equation say dy dt equals, like we did in the previous section, in the previous video. Or at this point you can start plugging in numbers. My guess is it's going to be a lot easier to manipulate this equation once you've got actual numbers in place instead of all these dx dt's and variables that we don't know what they're worth. So let's start plugging some stuff in. Let me get rid of these arrows. Alright, I'm going to zoom out so I can get these values. 2 and 5 for x and y. So x is the 2, so let me plug that in, times, I don't know what dy over dt is, that's what I'm going to be figuring out eventually, plus, now dx dt is a -3, so I already have a plus sign, so I'm going to put my -3 in parentheses, times my y value, which I just saw was a 5, good, plus dx dt again is that -3, alright, right hand side is still 0, great. Now should I try to isolate dy dt? Maybe not yet. Maybe let's do some multiplication and then combine like terms with that -3. So let's keep the 2 and times the dy over dt. And I've got plus a -15 here, which is really the same thing as -15, and then plus a -3, which is really like -3 equals 0. So while I didn't just put a minus 18 on the left-hand side right away, I'm definitely going to go ahead and add, that's a plus sign, 18 to both sides. And when we do, the left-hand side now only says 2 times dy dt. The right-hand side says 18. We can divide both sides by 2 to find that dy dt is 9. 9 what? I have no idea. It's maybe the part of this type of a problem that I like the least, is that I get an answer and I don't really know what it means. Well, it's the rate of change of y with respect to time. If you say it in kind of a snooty voice, it makes the 9 sound a little bit more important. But it's not important. I don't have any units. I don't know what's going on here. But it's the right answer, and I like that part. Alright, let's see what else we've got. This equation is very similar actually to the previous one. This equation has 2 variables in it, just like the previous one did. We're solving for dy dt, which means we need to be taking the derivative with respect to time, just like we did in the previous equation, which means we're going to end up with a bunch of unknowns like x and y and dx dt and dy dt. So there are 4 unknowns that we might end up with. And look at this. The problem gives us 1, 2, 3 out of 4 of those unknown values, and we'll be solving for the 4th one, just like we did in the previous problem. Okay, so I'm going to let you, well, it's not that so much that I'm going to let you do that one as, I mean, you could try it and see if you get some nice numbers. I don't know what the solution to this one is. I have not worked it out. But I will tell you that it's so similar to the previous one that, that I don't want to spend the time to do it in this video, but what is important is that you realize the similarity between this problem and the previous problem. In the previous one, we had to use the product rule. Here you're going to be using the quotient rule. In the previous problem, we were taking the derivative of x and y. Here we're taking the derivative of x squared and y squared. I will tell you, let's go through and take the derivative of the equation. I'll leave you to do the easy stuff like plugging in numbers. All right, I'm going to cruise through this one a little bit faster. Derivative on the left-hand side, quotient rule. So I've got the denominator, x minus y, times the derivative of the numerator, which is dx dt plus dy dt. I'll try to have good handwriting. Minus low high minus high x plus y times the derivative of the denominator, which is dx dt minus dy dt. So this is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. That's the quotient rule. All divided by, as part of the quotient rule, the denominator squared, that's x minus y quantity squared, equals, I did not leave myself quite enough room over here, so I'm going to have to write a little bit smaller. Derivative of x squared is 2 times x to the first power. Chain rule says must multiply by dx dt. And then plus the derivative of y squared is 2 times y to the first power. Chain rule says must multiply by dy over dt. So let me zoom in just for a moment on this part out here to make sure that you'll be able to read it, since it had to get real small out there. There you go. 2x times dx dt plus 2y dy dt. This is the equation that you need to be working with. You've got your 3 values that you can plug into it, a 12 and a 1 and a 0, and then go through the motions and eventually isolate and solve for dy dt. I think that what I just did for you is the most difficult part, so that is the part that you should use as an example, and go through and maybe rewind the video and pause it before I started writing anything out, and you try to find this derivative using implicit differentiation, and then you can push play and move through the video again and see if you got what I got. Because the next thing I want to do is go down here where we have some applied problems. So this is a revenue, cost, and profit section, This course that I teach is primarily, if not exclusively, to students who are in the College of Business. So often we see equations that involve revenue and cost and profit and marginal, all three of those. And in this problem, we've got a company that knows that the unit cost C and unit revenue from the production and sale of X units. Okay, that's a lot of information already. C represents cost, R represents revenue, and X represents the number of units sold. Okay, and those are related by this equation, which you might notice does not involve the variable X. Interesting. The first two problems that we worked with in this video, we took the derivative with respect to time, and time was not a variable in either one of those equations. Makes you wonder what we're going to be doing here. Find the rate of change of revenue per unit. I'll tell you, let me stop you there. That's a lot of information too, and it's kind of hidden. Find the rate of change. So when I see rate of change, immediately my mind says, okay, slow down. Rate of change usually means derivative, right? Change in y over change in x, rise over run. Okay, all of those are rate of change, slope, first derivative, same. So this time it's the rate of change of revenue, change in revenue per unit, and X was representing number of units. So I assume that we're talking about change in revenue with respect to change in number of units sold. That seems like a pretty reasonable relationship to be talking about. Your revenue is definitely going to be changing depending on number of units sold. Okay, and when the cost per unit is changing, I'm seeing the word changing again, by $12. So let's sort of focus in on this. Cost per unit is changing by 12. So it's the cost that's changing. So that sounds like DC to me, and it's changing per unit. I'm not just going to have an X floating around down there by itself. Certainly it's the cost changing as the number of units changes, and it so happens that they're telling us immediately that this is equal to 12, and it's not just 12, it's $12. Nice to have some units to go along with these numbers. So we're finding dr dx, we're given dc dx, and we're being told that the revenue is 4,000. Even I know how to translate that pretty quickly. To me, that says R equals 4,000. All right. I'm being given two unknowns, and I'm being asked to solve for a third one. I hope there aren't four unknowns once we take the derivative of this equation, or we might be in trouble. Let's see what happens. We're going to be taking the derivative of this original equation, c equals r squared over 112,000. It's a little strange. I much prefer it if it said c equaled 5r squared, because then I could take the 2 and multiply it by the 5, and I would get 10r to the first power. It's weird because the r squared doesn't really have a coefficient, so I think what I'm going to do is rewrite my original equation. And I'm going to rewrite it to say c equals 1 over 112,000 times r squared plus 5807. That way r squared has a coefficient. Okay, now let's take the derivative. And the derivative of c with respect to x is dc dx. And the derivative of our next term, we have to take the 2 from the exponent position and multiply it by the coefficient, so you get 2 over 112,000. And if you want to write that down, you can. I'm going to reduce it in my head so that it reduces to 1 over 56,000. And then I keep my variable. I decrease the exponent by 1, so now it says r to the first power, but the chain rule says I have to multiply by my inner function, the r value. And remember here, my r is different than the variable that I see in my denominator, which is the x, because we're taking the derivative with respect to x. I know to employ the chain rule, just like I did out here. Derivative of c, but it was with respect to x, so I had to use the chain rule. dr dx. And then if you want to put a plus 0, you can. That would be because the derivative of this constant value is 0. I will not be doing that, however. But what I am going to do is look at my new equation after having taken the derivative using implicit differentiation with respect to x, which sounds very fancy. Rattle that off to a friend or family member over the phone. Hey, how's your math stuff going? You tell them, well, I took the derivative of a function with respect to x in order to find the rate of change of costs and explore its relationship with the revenue and the rate of change of revenue with respect to the number of units produced. They might stop asking you questions about math, so if you want them to engage in that conversation, maybe don't hit them with that. But what I do notice in this equation is I've got 3 unknowns, and I remember from our earlier conversation that we were given 1 piece of information, 2 pieces of information, and being asked for the 3rd. So they've given us 2 out of 3 values. We've got 3 I like this. I think we're going to be able to find an answer. dc over dx, let's plug it in. There's the 12. And we're keeping the 1 over 56,000 for better or for worse. And we were told that r is equal to 12, so I'm multiplying by 12 and multiplying by dr over dx. I don't know what that is. That's what we're solving for. Oh, this is very nice. Look at how nice that's shaped up. The first thing I'm going to do is divide both sides of my equation by 12. And when I do, these 12s are going to cancel out, which means I end up with a 1 on the left-hand side. So don't actually cross those out. I don't ever do that. I would put a 1. Oops, that's a big 1. Let's put a 1 on this side. We've got the 1 over 56,000. Get that 6 in there. And the dr over dx is still in here. We're solving for dr dx. That's multiplication happening right there. I'm going to multiply both sides of this equation by 56,000 times 56,000. Left-hand side becomes 56,000, which cancels out with the denominator on the right-hand side, leaving me with just dr over dx. And what this tells me, and this is important, studies have shown just very recently that a lot of students who work through these problems get a numerical answer but struggle to interpret their numerical answer, in the context of the original question. So let's just take a moment to look at this. The right-hand side of this answer says dr over dx. Now the d is actually a lowercase delta, which represents change. So this is change in revenue with respect to dx, which is change in, this says sale of x units. So x represents number of units sold. So change in revenue with respect to number of units sold is 56,000. So you could think of this graphically, and if you had revenue on the horizontal axis, should we do that? Let's put revenue on the vertical axis and number of units sold on the horizontal axis. And if you think of this as 56,000 over 1, and you take that and you take it back to a college algebra class where we think of this as rise over run, this is a big change. We're changing the number of units sold by 1, and the resulting change in revenue is 56,000. That's dollars. Okay, so depending on the industry, if it's the candy bar industry, maybe that's a really big number. If it's the automotive industry, maybe it's not quite so large of a number. So I don't know, because I'm not in the College of Business, just how reasonable of an equation this is in order to describe the relationship between cost and revenue. But at the particular point in time where your cost per unit is changing by $12 and your revenue is $4,000, to see that you end up with a change in revenue with respect to a change in unit production of 1 being $56,000, I'd say that that's probably a number that somebody ought to know about. And I do have one more example for you. Again, I'm seeing a capital R and a capital C, which means I think we're talking revenue and cost again here. Let's give it a read. Given the revenue and cost functions, yep, there they are, where X is the daily production. Okay, so I've got R is in terms of X, because my R equals equation has X's on the right-hand side, and the C equals equation also is in terms of X. So X is the daily production. We want to find the rate of change, right? Are you hearing bells and whistles, right? To slow down, because we're getting to some good stuff here. Rate of change, that's not a highlighter. That's a highlighter. It's the rate of change of profit with respect to time. Let's just keep highlighting. And that's what we're supposed to be finding. So find, let's write a little note. Find rate of change of profit, that's dP, with respect to time, that's dt. dt. None of those two equations in the first part of this sentence involve t for time, okay? So that yells at me that we're going to be using implicit differentiation. When 20 units are produced, so X is representing daily production. So the fact that 20 units are being produced tells me that X is going to equal 20. And the rate of change of production, hello, rate of change. Rate of change of production is 4 units per day. All right, let's see if my yellow pen is very legible so that all this matches up. Rate of change of production, so that's dP. Is it dP? Rate of change of production is 4 units per day. Oh no, production is all about that X variable. This is dx. And it's per day. Days are a measure of time, so this must be dx over dt. And I know that that yellow is a little bit light, so I won't keep using that after this. Dx dt is 4 units per day. All right, so that's going to be equal to 4. I'm not putting units on it, but thankfully the variables tell me a little bit about units, even if I have to reference back to the original question, where, and I suppose we could highlight that in yellow also, X is the daily production, so it's number of units. Okay, so I think we've squeezed every ounce of information that we can out of this. Maybe it's time to start taking a derivative. Let's find out. So given these revenue and cost functions, we're trying to find dP dt. I don't see a P equals equation. I don't see the variable P anywhere. How are we supposed to do this? Let's keep reading. It's in there. Find the rate of change of profit. There's the P. How am I supposed to rate? Don't I need a profit function in order to find the rate of change of profit with respect to time? I think I do. Do we have a profit equation? We don't. Do we know how to create one? Yes. Profit, that's an R, that's a P. Profit equals revenue minus cost. So P of X, I was going to write P of X equals R of X minus C of X, but the notation that you're seeing at the top of your screen, this doesn't say R of X and C of X. I think it could. We could be using function notations, R of X and C of X, but it's not written that way in the printed problem, so I won't do that. I'm just going to write P equals R minus C, and let's tighten this up a little bit and write it as P equals, the revenue equation is 26x minus 0.3 x squared minus the cost equation in parentheses, must be in parentheses, 5x plus 11. And then let's get rid of these grouping symbols as we were taught. I never liked that. Eliminate the grouping symbols. Something about that just, I don't know. Get rid of the parentheses, grouping symbols. 26x minus 0.3x squared minus 5x minus 11. So I distributed this minus sign into my parentheses. Can we combine like terms? Let's put a little note out here. DIST and then CLT for combined like terms. And I'm going to sort of rearrange things a little bit so that this is a little bit more familiar to me. I'm going to put my squared term first, which is negative 0.3x squared. And then my x terms I can combine. I've got 26x minus 5x, which makes for positive 21x's. And then my constant value is negative 11. Now I've got myself a profit equation. Now let's take the derivative with respect to time. On the left-hand side, that gives us dp dt equals, and then take the exponent, multiply it by the coefficient. That makes for negative 0.6 times x to the first power. Chain rule means we need to multiply by dx dt, the derivative of the x function, plus this invisible exponent of 1 times the coefficient of positive 21 makes it a positive 21. And then you've got times x to the 0, which is equal to 1. And then you have to use the chain rule and multiply by the derivative of x. So we do have a dx over dt there also. And then if you want to put a minus 0 at the end, you can. I'm not going to, but the derivative of negative 11 is definitely 0. What unknowns do we have at this point after having found our derivative? I see the dp dt is 1, x is a second one, and dx dt is a third one. How many values did the original problem give us? I'm hoping 2 out of 3. Here's 1, here's 2, and here's the third one that they didn't give us that they're asking us for. Perfect. Let's plug in some numbers. X is 20, dx dt is 4. I'll leave those right at the top of the screen. And we don't know dp dt, that's what we're looking for. So let's fill in what we do know. Negative 0.6 times an x value of 4 times dx dt, which is 20, plus 21 times dx dt is 4 again. And from there, it is arithmetic. How much of this am I willing to do in my head? I know that a negative times a positive is a negative, and I know that 4 times 20 is 80, and 8 times 6 is 48, with a 0 at the end of it makes it 480, but it's a 0.6, so let's slide the decimal point back 1 and get 48. And then it's plus 84. Is there a trick for adding palindromes when one of them is negative? I have no idea. If there is one, I'd like to know what it is. Alright, now we need to do arithmetic, which is not my forte. This arithmetic gives us an answer of 36, I do believe, and that is dp dt. And then let's take a moment to think about what this actually means. Remember that the d's are deltas, which represent change, so we've got change in p, which means change in price, divided by change in time. So the rate of change at this particular moment in time says that the profit, P stands for profit, that our profit is increasing at $36 per unit of time. And what is our unit of time? It was mentioned here. It's the very last word. It's per day. So rate of change of production was 4 units per day. So that's where I got my unit of measure for time. But here P is representing profit because we built a profit function. So again, profit is increasing at $36 per day. And I recommend that you put a note in your notes that says $36 per day. Alright, my friends, that is an introduction to implicit differentiation as pertains to related rates, which is very often applied to problems where you're taking the derivative with respect to a variable that is not present in the given equation. Often that is the time value, but not always. And after taking the derivative with respect to whatever, in this case with respect to time, we ended up with an equation, this one, and the next thing that I did was I started plugging in my values. You can do it that way and then solve for the desired unknown, or we could have taken this equation, solved it for the desired unknown, and then plugged in values. In this particular problem, it was nice because the thing that we were looking for, dp dt, was already isolated on one side of the equation for us. As we've seen though, that won't always be the case, but just realize that you have the two options for the order in which to proceed: solving for the unknown or plugging in your variables. And remember to be careful all the way through the process, not just with taking the derivative and doing the implicit differentiation, but also with plugging in the numbers to the right locations and doing good arithmetic. You don't want to do all the complicated stuff and make a mistake on the easy stuff. Alright, I'll let you get to some practice, and I'll see you next time. Thanks so much.